Space, time, matter, the very fabric of reality. Understanding these fundamental concepts has been the holy grail of physics for centuries. From Newton's laws of motion to Einstein's theory of relativity, our view of the cosmos has evolved dramatically. Yet there are still huge gaps in our knowledge, mysteries that have eluded even our greatest minds. But what if the solution was right under our noses? Or rather, what if it was far smaller than we could possibly imagine? Thanks to breakthroughs in quantum physics, today's researchers believe the answers lie in the mind-bending realm of string theory, a theory where the universe's smallest constituents are not particles, but vibrating strings, strings that may exist in up to 11 dimensions of spacetime, dimensions that shape the laws of physics in our universe. If proven correct, string theory could be the elusive theory of everything physicists have long sought after. Let's break things down and explore exactly what string theory is, why physicists developed it, and how these tiny strings in hidden dimensions might just explain the universe. To understand string theory, we first need to go back to basics. What is matter made of? What are the elementary building blocks of the universe? For a long time, it was thought atoms were the smallest bits of matter. The ancient Greeks like Democritus theorized that all things were composed of indivisible atoms. Of course, we now know atoms can be further divided into even smaller particles, protons, neutrons, and electrons, and those particles can be divided again into quarks, perhaps the smallest units of matter, or so we thought. Thanks to quantum theory, we now know matter exhibits both particle and wave properties. Particles can act like waves and vice versa. This is crucial to string theory, because at an infinitesimally small scale, the theory says particles are not really dots of matter, but rather one-dimensional string-like objects. That's where the name comes from. These strings are thought to be around 33 centimeters long. That's about 1,000,000 billion times smaller than a proton. Too tiny for even our most powerful microscopes to observe. And these strings aren't still. They constantly vibrate at different frequencies and in different patterns, like the strings of a guitar vibrate to produce different notes. It's these different vibrational states that give rise to all the different fundamental particles. Electrons, photons, gluons, you name it. They're all just different versions of the same basic string, dancing to its own unique tune, so why strings and not something else even weirder? One reason is that string theory beautifully explains several mysteries that have stumped physicists for decades, like why gravity is so much weaker than other fundamental forces. Gravity seems weak because some of it leaks out into hidden dimensions. Wait, hidden dimensions? We'll come back to that mind blower in a bit. Another mystery explained by string theory is the elusive graviton particle. Attempts to detect gravitons have failed, even though theories predict their existence. String theory says gravitons are closed loops of strings, which makes them much harder to find. Pretty neat how strings can elucidate so many problems. Now back to those hidden dimensions. String theory says strings vibrate and interact not just in the 3 spatial dimensions we're familiar with, but in 6 more spatial dimensions that are completely invisible to us. Whoa, why so many freaking dimensions, you ask? Well, it turns out the math only works out if there are 10 dimensions total, 9 spatial dimensions, and 1 time dimension. 10 dimensions may sound crazy, but think of it this way. Imagine a 2-dimensional world occupied by 2-dimensional beings. They can only move left, right, and forward, backward. A 3-dimensional being could hover above their plane of existence like a ghost. The 2D beings can't perceive the 3D ghost dimension, even though she's right near them. Similarly, we 3D humans may be unable to perceive the 6 extra dimensions predicted by string theory. They exist at every single point in space, but are curled up at microscopic scales. This is how gravity leaks into extra dimensions. Gravity is weak because much of it extends into the hidden dimensions. Now, if this is all starting to make your head spin, don't worry. Even Einstein found more than 3 spatial dimensions hard to grasp. In fact, string theory began partly as Einstein's vision to explain electromagnetism through extra dimensions. He didn't invoke vibrating strings, but the basic idea was there. After Einstein, various physicists built upon the concept of extra dimensions. But it was 3 scientists in the 1970s who took the decisive leap to a full-fledged string theory. Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind invented string theory as we know it today, unifying quantum mechanics and special relativity into a coherent mathematical framework. an amazing achievement that required no experimental evidence at first. The math itself was so elegant, they knew they were onto something big. And the theory only got stronger as more physicists studied its implications. Fast forward to today, and string theory is one of the hottest topics in physics. There are still many variations of the theory being debated. Some versions have closed strings, others open strings, or a combo of both. The strings themselves may be made of supersymmetric particles. That's why superstring theory is a more fitting name than just plain old string theory. The math checks out in 10 dimensions or 26 dimensions, and the latest research focuses on vibrating membranes called branes instead of strings. Brane theory extends string theory into the strange world of quantum gravity and black holes. Yes, string theory also helps explain weird quantum gravity effects. So is string theory proven reality or just elegant math? Well, the unsatisfying answer is we don't know yet. To be validated, the theory must make testable predictions we can verify with experiments. This has proven difficult as strings are so infinitesimally tiny. Testing their properties requires particle accelerators more powerful than any built before. One prediction is the discovery of supersymmetric particles at high energies. So if such particles are found with the Large Hadron Collider or future colliders, it would be strong evidence for string theory. Indirect evidence may also come from astronomical observations like gravitational wave measurements that match string theory mathematics. Regardless of experimental validation, string theory provides a compelling framework to tackle the most perplexing enigmas in physics, from black holes to dark matter to the very meaning of existence. Some call it the ultimate theory or theory of everything, a unified description of the cosmos, one that marries quantum mechanics and general relativity into a self-consistent model of reality. While we don't have all the pieces of the puzzle yet, the prospect is exciting. Imagine a future where we truly understand how the universe operates at the most fundamental level. Of course, a complete theory of everything would have profound implications. It may reveal whether reality is deterministic or randomly probabilistic. It may explain the arrow of time and the second law of thermodynamics. It may tell us if the universe is eternal or had a distinct beginning. Maybe it will even answer the age-old question: what is the meaning of life? Yet until the day comes when string theory is proven right or wrong, the journey itself unlocks many insights, pushing the boundaries of human imagination, testing the limits of mathematics, revealing just how strange and complex the universe could be. Things once dismissed as sci-fi fantasy, extra dimensions, vibrating strings, multiple universes, may actually be real. String theory and its successors embody the unquenchable human desire to understand reality at its deepest level. From ancient Greek atomists to modern quantum pioneers, our models evolve, but the quest remains the same: to find order amidst the chaos,